Hi, welcome to the pre-calculus lecture series. And today, this video, we're going to talk about section 4.3, the logarithmic function. So the log function is one of the very, very important functions and which, have big applications in the calculus. So that's why, for this chapter 4, we talk about the exponential and the log. They are both very, very important, in the calculus and was frequently used functions. Okay, so now let's go to our lecture notes and let's start to talk about what is the log functions here. Okay, so let me go to my lecture notes here. Okay, so for the log function, so the first, let's take a look at what is the definitions of the log functions here. Okay, so the first things here, let's try to see here. So the log function definitions here. So we use this notation. We say the log a, okay, and the x equal to y here. So what is this a here? This is the a. We call this the base of this log functions here. Okay, so I cannot have a negative basis here. So, and so here the a has to be positive, and a cannot be equal to 1. When you see this, and then you say, whoa, this is kind of like some similar requirement for the exponential function. So let's take a look at what is this relation to the, the exponential functions. Okay, so the way if you write these ones here, so from the exponential function, so you will write this is the a, then the y, and will be the exponents, and this is the x here. So this is how do we define. So like if you say log a x equal to 2, what's that means here, right? So that's why let's take a look at some simple examples here. Let's say the log 2 here. Okay, so let's say log 2, and so here is if I want to find the x value that is equal to 3. So what's that mean? That means, you can see here, this is my base, right? So this is exponents here. This is the exponents here. So now based on my definition about the log functions, so I know that this is 2 to the 3rd power, right? So in here, be very careful here, I'm color coding that, right? So that's why, okay, so that's why 2 to the 3rd equal to x. So what is my x here? X is equal to 8, right? So that means if you rewrite this log function, you will say it's log 2 to the 8 equal to 3. Okay, so that is what we define the log function. It really is the relation with the exponential functions here. Okay, so now let's take a look at a few very, very key properties here. So so let's take a look at the properties number 1 here. Okay, so let's take a look for any basis here, right? So a, if my log function is equal to 1, then what is this values here? Okay, so let me say, I say this is my y values here, right? So based on my relation to the exponential function, so what is that tell you? So the a to the what? Y's power equal to x here, right? So in here, the x equal to what? X equal to 1. Right? Okay, so that means what is the power, exponents of the power will give you 1. I know is what? I know the a to the 0 anything to the 0 power is equal to 1. So what I have here, so I have y equal to what? Y equal to 0. Okay, so this gives us one very important properties here. So the first one's here, if anything is a log function is 1, it's going to be equal to 0. And you show is we always go back, try to use our exponential function to show it. Okay, so now let's take a look at the number 2 here. So if this is log A and A, what is this value here? Okay, let me say this one is Y again, right? Okay, let's see how do we get it. So this is A to the Y's power equal to A, right? So what is this A? A is really is what? The first power. So you know, okay, they have the same base. So basically you cannot remove the base. And so what is your Y values here? Y value is equal to 1 here, right? Okay, so this one we got our second very good property. So 1. So that means if here and the base the same, it's kind of like you can cancel that each other. So it will become 1 here. Okay, let's take a look at property number 3. Those are very handy properties here. Okay, so here, this is log A to the A, the power. Okay, let's see what is this one equal to. Let's say it's equal to Y. Okay, so now the same way I use my exponential properties here, right? So this will be the A to the what? Y's power equal to A to the what? X. Okay, so now you say, oh, they have the both have the same base. I can cancel that out. And so what do you have here? You have Y equal to X. Okay, so we have our another very good properties here. This is equal to X. So just like this is kind of an extension of the property number 2. So you see here, they are the same. So since you can just cross out the whole thing will become X here. Okay, so now let's take a look at the last properties here. So let's say e to the log, okay, and I'm sorry, not e. So this one's here is a to the log ax. What is this one will be equal to? Okay, all right. So now I'm going to use the exponential, right? So I'm going to use this exponential definition, try to find my solutions here. Okay, so this is a to the y. So this is my what? This is my y's, right? Okay, a to the y equal to x here. So that's why I'm going to try to find the x here. So let's take a look. Okay, so now I go backward to the log function, right? So you see here, this is log to the y equal to x, right? So this is use exponential function definitions here, right? So this is use this exponential function definition. Now I put it back here, right? So now I will say this is the log, right? The log, what is the base? A. Log x here. So it's a log, so it will be the red x here. So the log x equal to what? Equal to y. So what is my y's here? It's log ax here, right? So the log x is equal to the log ax here. So that is my y's here, right? So then I have here, so this is my y's here. So that's why the whole thing is going to be what? Will be x here, right? Okay, so here I finally get my answers here. So this is red x here has to be x, right? Because they have the same. You say the red x and this x, right? They're the same here. Or maybe I shouldn't, this color get the color out. So this red x, why I go to red x is equal to this green x. So that's why I know the red x is finally I get my answer is x here. So other way you can look at it is you see here, right? You can cancel that out because this is log a and a, right? So this is like a base the same. So you can cross that out. So we get the x here. Okay, those are very, very important properties. It will help you a lot when you try to simplify the log functions here. Okay, now let's take a look. Okay, so what is the answers for here? Okay, so here we want to find the log ax. So let's assume, okay, so we use these notations, right? We use that. So this is y. Okay, so that means ay, so a is my tens, right? My base here is a tens here. Okay, so ay, so it's a 10 to the y is equal to what? To x, right? So the inside here, let me color coding that. So it will be, so this is the inside here, right? So this is the x here, okay? Okay, now let's try to do that. So it will be equal to 1,000. And I know the 1,000 is 10 to the what power? Third powers here. Now they have both, they have what? They have the same base. Then you can remove that and then you will find the answer. What is the answer here? Y equal to 3, right? Okay, so that's why the answer for here is what? Okay, so this is what the answer here is 3 here. Okay, so let's try to do one more, couple more. So let's get very familiar with this. So this is the log base 2, right? Okay, so log base 2, we do the same thing. We say y here. So that means 2 to the y is equal to 32. And in order to solve for y, you need to have come out with the same base. So 32 is 2 to the what? 2 to the 5th power, correct? Okay, so then you say, okay, now I can cross out the same bases here. So what is the y here? Y is equal to 5. So that is where this answers here. Y is what? Y is equal to 5 here. Okay, now let's take a look at the next ones here, right? So this one's here, first circle your base. So this is the base, it's a 10. And I am looking for the y's here. So let's do exactly the same thing. We use exponentials, right? So this is a 10 to the y is equal to 0.1. Oh boy, it's 0.1. Okay, so I know I need to get the same bases, right? So 0.1, what is the 0.1 here? The 0.1 is 1 over 10, right? So what is 1 over 10? 1 over 10 is 10 to the what? Because this is the first power on the denominator. So when you flip it, what is here? It's negative 1 here. Ta-da! So we get what? We have the same base. So now I can cross out because the same base. So what is my y value? My y value is equal to what? Negative 1 here, right? Okay, so that's why I got my answers here is what here is a negative 1. Okay, it's fun, right? Okay, so now let's take a look at our last practice. This one here, this is 16th here, right? So this is my base 16. So the same thing, I let this is equal to y. Okay, so then here 16, so that means 16 to the y equal to 4, right? So 4, this is for the first power. Now I need to change it to the same base. Okay, so I saw the 16. Oh, 16 is good. It's 4 to the what? Square, right? So this is y. So this is the fourth power. Now what is here? Haha, so this is 4 to the 2y equal to the 4. Ta-da. So I get a what? I got the same base, so I can cancel that out. So what is my final answers here? My final answer, I have a 2y equal to 1. So what is y is here? Y is 1/2 here. Okay, so here, this is the y equal to 1/2. So how to find the log function values is very important, right? So you need to basically use the exponential, try to find it. Okay, so now in here, the next example, let's say, evaluate the following by using the logarithm properties here. Okay, so here, let's see what is the logarithm property here. The first one here, we say anything is 1, right? Doesn't matter what is the base. So what is here? This is 0. Okay, so the next things here we say, if the base and your function value is the same, so what is the answer? Well, the answer is 1. Seems like, just like we talked about, seems you can just cross that out, right? Okay, so the third ones here, they said log 5 and 5. So, oh, this is a base 5, this is a 5. Kind of, I can just cross that out. So what is the answers here? Is 8, okay? Then here, the last ones here is exponential. So this is a 5, and this is the base is 5. Oh, good. I can kind of cross out here. So what is the answer? The answer is 12, right? So by using the property, you can get the answer very fast here, right? So it's very good. So you need to remember that. If you don't remember, that's fine. You need to know how to put it back to the exponential and derive it, right? Okay. Okay. So the next things here, we're going to talk about the graphs of the logarithm functions here, okay? So this is also is very, very super important topics here, right? So let's say I have y equal to the log ax here. So what is the function of the logarithm? Okay, so the functions of the logarithm functions here, okay, so the function of the logarithm, okay, so this is x and this is y, right? So the logarithms here is this type of the function. So when you plot it, it's going to go like this. Okay, so that means that this point is going to continue getting closer and closer and closer to the y-axis here. And now we have one key critical point, key points here to help us to identify the log function. So what is this point? Is 1, 0, right? Because we know when from the property of the logarithm, what happens here? You're going to have an x-intercept here. So from here, we come out with a very important definition. So the domains here, so the domains here for the logarithms here, it has to be greater than 0. That means the domains has to be from 0 to infinity. Because this is the asymptote, so this is the parentheses here. Okay, so it cannot be equal to 0. If you do not believe, you use your calculator and put like a negative number or 0 in your calculator. What is your calculator going to tell you? It's going to tell you is error. So the domain of log function has to be from 0 to the infinity. Now, the range is here, right? The range is y value. You go like this. So what is the ranges here? Is going to from where to where? It's going to y value, right? So it's y belong to the all real numbers, right? So it's from the negative infinity to the positive infinity. So you can write it's negative infinity to positive infinity. Of course, we talk about that this is the key point, right? 1, 0. Then for this province here, for this log here, we also have asymptotes, right? Because this leg, the left leg, going to get closer and closer to the y. So we have what type of asymptote? We have vertical asymptotes, right? So what is the vertical asymptotes here is y-axis. So y-axis is my vertical asymptote. Also, the y-axis you can write as x equal to 0, right? So that's the asymptotes here. And also, if you remember, I don't know, you remember or not in the exponential functions, right? So we said the exponential, the rate of the change. Let's do this. All right, so we said in the exponential, if you don't remember, you might want to go to review. So we know the rate of the changes. Okay, so we say the exponential is what? Exponential is the fastest ones, right? So this is the fastest. So this one is faster than what? Power function. Right, so for example, like our polynomial is power function is something x to the nth powers, right? Then compare to the power function, then the logarithm. So log functions here is a little bit slower than the power functions here. So that's how do you, if you want to hear the rate of the changes, right? So that means that you can do a kind of a pictures here. It's kind of like go like this way. So this exponential, this is the fastest. Okay, this is faster. Then it's going to go faster, and the power is going to be faster. Then the power function is going to be faster than the logarithm functions. And the reason why it is, and so you can use your graph calculator to see that. And this is a kind of important ideas also, right? The reason why it's important because when you go to calculus and when you try to find the limit, you're going to use those properties here. Okay, so now let's also think about it. So if you have a different bases here, right? So this is the one with the base is what? Is base A here. So if I have a base B here, right? So let me see here. So if I have a base B, if I have a log function go like this is a log base B x here, okay? So if if this function goes slower than the a's, right? So in here is just the opposite, like the exponential. So what here we said here, so the a has to be less than b. So if this is log base 2, then this is log base 3. So log base 3 going to go a little slower than the log base 2. So we covered this a lot, good information in this note. So you have to know the domain and the range. Be careful the domains, right? Here cannot equal to 0. Then also you need to know the vertical. So very important concept of vertical asymptote and also the rate of the changes, right? So the rate of the change, which one it changes faster. And those are very useful things later on you go to the calculus here. Okay, so now let's take a look at the problem numbers, example number 3 here. So let's say, hey, sketch the graph of each function, then state the domain, range, and asymptotes here, right? Okay, so let's take a look at the A. So so let's start from what? Okay, so we always start from the parent functions, right? So here, let's take a look at the parent function. So this is the parent function. So this is the parent is log 2x, right? Okay, so now let's try to write here. So we said that this is the 1, is the critical point. So I know my function going to go like this. Am I right? Okay, so I know my function going to go like this. And then, okay, so because I have a negative inside here, so what type of the transformation is this negative here? This is right, what is reflecting to what? To the x-axis, right? Because you have a negative number. Okay, so now that means I need to bend these things, kind of is symmetric to the negative numbers, right? So that means my things are going to start like this. Correct? So this is my new log function because the positive going to go boom, change to here. This one go boom, go up here, right? Okay, so now this is my final function. This is gx equal to negative 2 log 2x here, right? Okay, then let's say that that is find the what is the domains here, right? So let's see here domain. So domain still the same, right? So it's from where? 0 to infinity, right? So still from domain. What is the range here? Well, I just flip over the x-axis. So the range still is from the negative infinity to the positive infinities here, right? So what is the asymptotes here? Oh, I still have a y-axis. So I still have a vertical, what? Asymptotes, right? So I still have x equal to 0, the vertical asymptote. So you flip over the x-axis, it does not change much, right? Okay, so now let's take a look at part B here. So part B, this is my okay. So now my parent function. Okay, so my parent function will be start the same way. They are log 2x. Okay, so here this is my critical key point. So my parent function go like this, right? So this is put the dot lines here. So this is my parent function. See here. All right. So now you have this one inside negative x. So what is this negative x means here? That is what? This is reflecting to what? Reflecting to the y-axis, right? Okay, so now that means I need to boom, bend over to the y-axis. So first, this point go to the negative 1 here. So my function going to be like this, right? So this red one, so this is my final functions here, log negative 2 and the negative x here, right? So that's what is the after transformation. Okay, so now let's try to find the domain here. So the domains here right now will be these red functions, right? So what is my domains here? From 0 to the negative infinities, correct? Okay, can I touch 0? No, I cannot touch 0. So it will be the negative infinity and 0. So what I have here is parentheses, right? So how about, do I have domains? I'm sorry, the ranges here. Oh, yes. So what is my range values here? My range here is the y value. So y value still is from the negative infinity to the positive infinity. So I have here is a negative infinity to the positive infinity. Do I have an asymptote here? Oh yes, I do have an asymptote because this graph is going to get closer and closer to the y-axis. So what type of asymptote I have? I have the vertical, right? So I have vertical asymptotes, right? So what is the vertical asymptote? It's the same thing. It's a y-axis or it's x equal to 0. Okay, and so that's it. Okay, so it's very important. Okay, so now the next ones here, I cannot emphasize more. This is also is very, very important, all right? Okay, so in here, we're going to talk about two specific, special, the log functions here, right? So it's a common log and the natural log. What are they? So we say the log function from the definition is log ax equal to y, right? And these ones here, this is the base. You can have any number, any positive number not equal to 1, you can be the base. So what is the common log? So common log, that's the log function, the base. I have a very, very special value. What is this special value? It's 10 here. Okay, so that is, if you see a base is 10, that's what we call it, the common log. So what do we write here? So we say that means the log, I have a base what? Base 10, right? So it's a base 10 x here. And also, if it's the common log base 10, typically we do not write the base. So you will write this is like a log x here. So like in your calculator, typically going to have two keys here. One is like you have a key is a log, and other is your key is ln here. So if you see the key log, that means if this log function, every log function should have a base. If you see this log function has no base, you immediately know this is a common log. That means the base is equal to 10, all right? So it's super important, right? So that's why in your calculator, when you see a log x, what's that mean? That means it's the common log here, right? So be careful the word common log. If every log function have a base, if you don't have a base, then if you see sometimes the people write it, there's no basis here. So what's that means here? That means this is a common log here, right? Be very careful. Okay, so the next ones here for the natural log, we have also, this is one of the probably is the most frequently used functions, right? In the calculus. So that means I have a very special base also. This base is this natural log value E. That means it's 2.712a something, right? Like that. So I write like the log E x here. So in order to simplify it, because also this is so commonly used, so instead of say the log E, I put the ln x here. Okay, so that is, so you put an ln, so that means it's log E. So that's why in the most of a calculator, even like a $5 one, when they have the log function, they typically have a log or ln. So you see the key ln's here. What's that means here? That means you have what? So that means you have the base is e's, right? So like in here, so if a lot of time you see, say there is a natural log x equal to y. What's that mean? Right? So it's the same, right? Because I know the natural log is the base of the e's, right? So this one's here, it really is just say what? Is the e to the what? Y's power is equal to x. Correct? So that is the, that's what we call it the natural logs here, right? Okay, so now you just need to recognize if you see a natural log, what's that mean? That means it's the base is here. Okay, so we talk about the general properties of natural log. So in here, with for the logarithm, so we're going to talk about a specific property for the natural log. It's the same. It's just like help you to recognize here, right? So here, this is the natural log 1 is equal to what? Oh, we say the natural log 1. So the reason why sometimes we say, okay, natural log y really is log e to the 1. And from the previous, we know anything to the 1 is what? It's 0. So be careful. So it's zeros, right? Then the next ones here we say is natural log e. What is that? So the natural log e, so you can say here, you say, hey, the natural log e, really, what is the natural log? Hey, it's log e to the e. So we say, oh, okay, from the previous, I know these two basically, I'm sorry here, that's the, okay, so here, that means that this is log e, right? So basically, if you see the E and the E, basically you kind of can cross that out. And because this E is power 1, so what is here is 1. So natural log E and E, they kind of bump each other out, right? Okay, so now it's follow the same idea. So natural log EX is here. What is this one going to be? So the natural log EX. Oh, so I can rewrite this is log e to the ex. Oh, good here, right? So this is kind of, you can cancel that out because the e and the e, the same base. So what is the answers here? So it's x here. Okay, so last times here, so e, the natural log, x here. What is this ones here? So the same things here. So this is the e, the natural log x is e log ex, right? So I know, that in here, because the e and the log e, because they have the same thing, they can cancel. So what is here? Is x here, right? So you just need to be, like, because a lot of people when they see the ln, they got it scaled. So just remember, those are the two common log functions. All right. Okay, let's take a look at some of this. Okay, and some of these examples here. So they said evaluate these ones here. So basically, these ones tell you here, right? So this one tell you the property of natural log. So every time natural log and the e, when they see each other, they cancel, right? They kind of cancel out here. So like, so now let's take a look at what is this one. It's natural log and the e. Hey, they bump each other. So what is the answers here? L, that is 8, right? Okay, so this one's here. I have a natural log 1 over, but I know I have a good property if a natural log bumping to the e can cancel. But I have this 1 over, it's not, directly, so I can change that. So this is natural log. So what is the e to 1 over e squared? So this is e to the what? -2, right? Because I can flip the denominator so the exponents will become negative. Then I say, oh, good job, because then the natural log and the e, they bump to each other. So what is here? Hey, so this is a 5 here, -2 is here. Okay, so the last ones here, basically they just, this problem just want to try to use your calculator. So put it into your calculator, use the key ln, to see, you will be able to get the same number as I have here. So it's 1.609 here. It's close to these numbers here, okay? All right, so now the last things here. So the domain for the natural log is the same as the typical logs here, right? So we say, find the domain of the functions, okay? So that means because this is log functions, right? So what happened to the domain of the log function? So we know 4 minus x squared has to be from where to where? Has to be greater than 0. Am I right? Okay. Okay, so that has to be greater than 0 here. So now I can add x squared both sides. So what I have here, I have x squared less than 4. All right. Now what I need to do, I need to take the square roots, right? So take the square roots both sides. So what I have x less than 2 and x greater than -2 here, right? So this will be my domains here. So here, that's why I can write it 2 and 2. So be careful here, right? You have it's a greater than sign. You cannot have an equal sign. Okay, that's it. That is the definition about the log function. Like I said, it's probably one of the most important functions in the calculus. You have to get very good at it, right? So the first video about this log functions, we basically talk about the definition and several very good properties. So remember, right, the natural log and the e, they kind of like they cancel each other out. That's good. And also we need to know the domain and the range and the asymptotes here. All right. Okay, that's it. And I hope you like this topic, and I certainly really like the log function. Okay, so that's it. And I guess I talk to you in the next video. We're going to talk about some other logarithm law. What type of the laws like we have for the logarithms here. Okay, sounds good. You have a good day. Okay, bye bye.